In this lesson, we're looking at exponential functions, and exponential functions are of the form y equals a times b to the x. So we've got that same a value that we've seen with almost every function. We have that a value out front that's going to determine whether this thing is going to open up or down or be stretched or shrunk vertically. Okay, so keep that kind of stuff in mind. And then the b value is just another constant term that's being raised to a power. And notice the exponent here is where we find our variable. So the x is actually the exponent, and that's really the defining characteristic of an exponential function, is that the variable is now in the exponent. This is the first time that's happened for us before. Now, there's a couple stipulations that we need to apply to this. First of all, a can't equal 0. And that should make sense. If you plug a 0 in for a, you have 0 times b to the x. Well, 0 times anything is 0. So what we would really have, if a was 0, is y equals 0, okay? Which is not an exponential function. That's a linear function. In fact, it's a constant function because it's the equation of a horizontal line, all right? So it doesn't form the pattern that exponential functions are going to give us. The next thing is that b has to be greater than 0. In other words, b has to be positive. If I plug a negative value in there for b, think about what's going to happen as the x value changes, all right? If I have a negative value raised to an even exponent, it's going to give me a positive number. If I have a negative value raised to an odd exponent, it's going to give me a negative number, all right? So what's going to happen is if b is a negative, my values for y are going to keep jumping back and forth between positive and negative values. It's not going to follow a proper pattern here. The graph is going to be all over the place, okay? And so it just doesn't make sense if we treat it that way, all right? So keep that in mind. The b value has to be positive. And then the other thing is the b value can't be 1. 1 would be kind of boring because I'd have 1 raised to a power. Well, 1 raised to any power is just 1. And so if b is 1 and I have 1 raised to any power is 1, what I really have is a times 1, which is a. All right. So if the b value were to equal 1, what I would really have is y equals a, which once again is a constant function. All right. It's the equation of a horizontal line, not an exponential function. All right. And really, these restrictions are kind of obvious as we start to work through these things. As we start to deal with exponential functions, these are going to be pretty apparent that these couple things have to be true. All right, so not something we really need to be super concerned with. They're kind of going to take care of themselves. All right, so if I look at this first one, if I want to graph this thing, I've got y equals 2 to the x. All right, this is a very basic exponential function, and keep in mind it is in that format. It doesn't quite look like that format, but really it's this. It's y equals 1 times 2 to the x. See, 2 is the thing being raised to the power, so that's the b value. The a value is actually a 1 this time. All right, and we can see x as the variable in our exponent, okay? So I'm just going to use my typical values that I use for an xy chart, -2, -1, 0, 1, and 2, and see where that leads me. Just be careful when you plug this in. Right here, if I do 2 to the -2nd power, keep in mind negative exponents means I send that thing to the denominator, so that would be like 1 over 2 to the 2nd power, which then 2 to the 2nd power is 4, so it's 1/4, all right? The easier way to do this, and the way we should be doing it as we get better and better at these, is really if I see 2 to the -2nd power, I'm going to say, well, 2 to the 2nd power is 4, so 2 to the -2nd is 1 over 4, okay? So I'm just going to go through that process very quickly and immediately write down a 1/4 over here, all right? I can do the same thing with the next one. If I were to take the next one and raise it to the -1st power, so 2 to the -1st power, well, 2 to the 1st power is a 2, so 2 to the -1st power is a 1 over 2, which is 1/2, okay? And it's just that simple, all right? 2 to the 0 power is the next thing I want here. 2 to the 0 power, anything to the 0 power, remember, is 1, so that's going to give me a 1. 2 to the 1st power is a 2, and 2 to the 2nd power is a 4, all right? So I plugged each of these in, and now I'm just going to plot them on my graph. So let's see, -2 1/4 is down here somewhere. -2 1/2 is right here. Sorry, I can't count. Let me try that again. -2 1/4 is here. There we go. And so I plot each of these things, and it gives me this graph, okay? And it looks like I've got some kind of curve forming. And the question really is what it does on each end. Well, when we think about this, if I keep going further and further in the negative direction, I'm going to keep doing 2 raised to a larger and larger exponent, but that larger and larger exponent is going to be in the denominator, which means I've got a fraction that's getting smaller and smaller and smaller and smaller, okay? So at this end, it's going to get closer and closer to 0 because it's going to keep getting smaller and smaller. On the other end, it's pretty obvious what it's going to do. If I keep plugging in larger and larger values, the numbers are going to get larger and larger and larger, so this thing's going to keep going up, all right? So this is an example of an exponential function, and really, more specifically, it's an example of exponential growth. Okay, exponential growth is essentially when the function increases from left to right. All right, so an exponential function in which y increases as x increases, really that's just saying it's increasing from left to right. The function is increasing the entire time. All right, when we talk about increasing versus decreasing, we always go left to right. This one is always increasing, so it's an exponential growth type of function. All right, so this is an example of exponential growth. If I look at the next one, again, if I apply the same things, we can kind of see that this is y equals 1 times 1 half raised to the x. So I can see the exponential function. I can see the different pieces of the exponential function. And now from here, I'm going to plug each of these in. So right here, -2, well, 1 half to the negative second power. Well, let's think of it this way. 1 half to the second power is 1/4. I just square each piece. So 1 half to the negative second, I take that 1/4 and I flip it. It's going to be 4 over 1, so just 4. Okay. 1 half to the negative first power is going to be a 2. 1 half to the 0 power is 1. 1 half to the first power is 1 half. And 1 half to the second power is 1/4. So I'm just plugging in each of these values for my XY chart. And now I'm going to plot these things. So let's see, I've got -2 4s up here. So I just plot each of these ordered pairs. And it looks very similar to what I got before, and it's going to follow the same kind of patterns that I got before. This thing's going to get closer and closer to 0 on this one. It's going to get bigger and bigger on this end. This is an example of an exponential function, but more specifically, this one is what we call exponential decay. All right, an exponential decay is an exponential function where y is decreasing as x increases. In other words, as I go from left to right, the function's getting smaller and smaller. Okay, so the function is decreasing the entire time. So again, increasing, decreasing. I always go left to right. This one from left to right, it's the function's going down, so it's decreasing. This is exponential decay. And when we look at these, we can probably take a pretty educated guess as to what really affects whether or not it's going to be growth or decay as I look at these two examples. When you look at these two examples, they both had the same a value, but look at the b value. Here I have a b value of 2. Here I have a b value of 1/2. And that's really what's going to separate these. Exponential growth is always going to be b values that are bigger than 1. So these are b values that are greater than 1. And exponential decay, down here, exponential decay is always going to be b values that are between 0 and 1. And actually, I shouldn't have that equals 2 sign in there because b can't equal 0. Okay, so these are going to be proper fractions. So keep in mind, if you want to make a note to that about that somewhere, it's easy to tell the difference between growth and decay when you look at the equation based on the b value. Okay. For example, if I look at this guy, this one you can tell right away this is going to be exponential growth because the b value is greater than 1. I have an a value of 3 this time, and keep in mind, think about what that a value is going to do. I could try to graph this even without the XY chart. Keep in mind, my original graph, don't write this down, but I'm going to show you the original graph that I drew that was that had an a value of 1 looked like this. So if I change the a value to a 3, it's going to stretch this thing vertically. I'm going to triple all these heights. So here, instead of a height of 1, I'm going to have a height of 3. Here, instead of a height of 2, I'm going to have a height of 6. The next one, instead of a height of 4, I'll have a height of 12. It's way up here somewhere. This one, instead of 1/2, I'm going to multiply that by 3. That's going to be 1.5. See, so I'm kind of tripling all of these. The 1/4, if I triple it, that's a 3/4. And so basically, this thing's still going to kind of do the same thing it did before, but it's going to do it much faster now. All right. So I'm kind of stretching this thing vertically. And I can easily confirm this by plugging a couple values in. If I plug the -2 in, that's a 1/4 times 3 is a 3/4. The -1, that's a 1/2 times 3 is a 3/2. The 0, 2 to the 0 power is 1 times 3 is a 3. 2 to the first power is 2 times 3 is a 6. 2 to the second power is 4 times 3 is a 12. And you see, those are the values that I just graphed, okay? But again, I'm stretching this thing vertically. And it's just like any other function. Once I've seen one of them, it's like I've seen all of them, okay? So that's what this one's going to look like, and I can get rid of this one in red. But notice a couple different things here. First of all, it's increasing, so still exponential growth. That's only affected by the b value. But also, we still get closer and closer to the x-axis without actually touching it. All right, these values are going to keep getting smaller and smaller. It's going to be smaller and smaller fractions, but never going to equal 0. Okay. So now if I look back at those first two functions that I graphed, that exponential growth and that exponential decay, I should notice something very distinct, a very distinct pattern as it pertains to the y values here. See, the x values are counting up by 1s, so we look at those y values, and we should notice here, as we look at it for a little bit, maybe you see it already, maybe you don't, but what happens here in this first set, to get from one y value to the next, I'm essentially multiplying by 2. See, 1/4 times 2 gives me a 1/2. And then 1/2 times 2 gives me a 1. And then 1 times 2 gives me a 2. And then 2 times 2 gives me a 4. And if I wanted the next y value, I would multiply by 2, and I get an 8. And then I'd multiply by 2 and get a 16. And if I wanted to work backwards, of course I could divide by 2, and I could go this way and get a 1/8. Okay, so that's the pattern that we should find we have when we're dealing with an exponential function, is that to get from one x value to the next, or one y value to the next, I'm just multiplying by a common term, and we call that a common ratio. If I look at the next one, it's the same thing. The pattern that you might notice here is you might think, okay, I'm dividing by 2 to get from one term to the next. So I'm dividing by 2 each time. All right, but we don't want to think of this in terms of division. So let's try that again. Instead of saying dividing by 2, we're going to say we're multiplying by, well, we're multiplying by 1/2. So to get from 4 to 2, I multiply by 1/2. From here to here, I multiply by 1/2. I multiply by 1/2. I multiply by 1/2. And beyond just realizing that we're multiplying by a constant term each time to get from one term to the next, I should notice also that the term I'm multiplying by is my b value. See here, the b value is 2, and I'm multiplying by 2 each time. Here the b value is 1/2, and I'm multiplying by 1/2 each time. And the other thing I should notice here is that right here, 0, 1, that's my a value. Remember, the a value is the thing that's out front, times 1, times 1. And so really I have all the components of my a, my b, all the components of my exponential function kind of within the context of this thing. Now the a value is not always going to be the y-intercept like that, but if we're in that standard form and we're not adding or subtracting values inside or outside with x to move or shift this thing, then that will be true, okay? And so the thing we look for if we're trying to determine if we're dealing with an exponential function is we basically look for the common ratio. We see if we're multiplying by the same thing each time. If we're multiplying by a common ratio, it means we're dealing with an exponential function. And then to take that further, we can immediately identify the b value, and most of the time we can identify the a value as well. Okay? So when I look at something like this guy, I want to know, is this an exponential function? So I just have to look at this thing and say, okay, am I multiplying by a constant term each time? So right here, to get from a negative 1/3 to a negative 1, I would have to multiply by 3. Okay, so now I check. Negative 1 times 3, does that give me a negative 3? Yes, it does. Times 3, does that give me a negative 9? Yes. Times 3, a negative 27. So I see that I have a common ratio, which means, yes, this one is an exponential function. So if I was asking, is this an exponential function, the answer is yes. And then to take that further, if I wanted to write the equation of this, it would be y equals, well, the b value here is 3 because that's the thing I'm multiplying by each time, so it's 3 to the x. And then I can see the y-intercept is actually a negative 1, so that would be times a negative 1. All right, that's my a value essentially. And so I can almost come up with the equation of this thing, barring any unforeseen values that are being added or subtracted to shift this thing. Okay? If I look at the next one, again, I want to determine, am I multiplying by the same thing each time? So to get from 1 to 2, I would have to multiply by 2. To get from 2 to 6, I would have to multiply by 3. To get from 6 to 24, I would have to multiply by 4. So there's definitely a distinct pattern here. I'm multiplying by 2, then 3, then 4, probably multiplying by 5 next. But I'm not multiplying by the same thing each time. It's not a common ratio, so that means this one is not an exponential function, okay? It's something else entirely, and probably something that we don't have the knowledge to write the equation of quite yet, okay? If I look at the next one again, am I multiplying by the same thing each time? To get from 1/8 to 1/2, I would have to multiply by a 4. To get from 1/2 to a 2, I would have to multiply by a 4. To get from 2 to 8, it's times 4. To get from 8 to 32, it's times 4. So I'm multiplying by the same thing each time, which means, yes, this one is an exponential function. And to take it a step further, it would be y equals, well, 4 is the thing I'm multiplying by, so that's my b value. The a value then is actually going to be my y-intercept this time, which is the 2. Okay, so it's y equals 2, 4 to the x. All right, I've got my a, I've got my b, and I can generally come up with the equation when I have just those couple values. Okay. In the last example we have here, just a quick word problem, and it says that we have 30 beetles are left undisturbed in a warehouse bin. So we've got some beetles, and they're going to go ahead and multiply while they're stored in that bin. We're going to have an infestation of beetles here, but the population doubles each week. So it models the function f of x equals 30 times 2 to the x. And there's a couple interesting things, first of all, about this equation. The first thing we notice, let me write it again down here, f of x equals 30 times 2 to the x. The first thing we notice is the initial population, that 30 beetles, is right here represented by my a value. And when we really get into word problems here and we start talking about exponential growth and decay, that's what we're going to find. That a value is our initial amount. It's what we start with, and in this case it's the 30. And then doubling each week, telling us what we're multiplying by each time. Remember, that's our common ratio. That's our b value. So the b value is the common ratio. It's the thing we're multiplying by each time. Okay? So even if I didn't give you this equation, I could give you this problem without the equation, and we should be able to come up with it. Okay? And that's what we'll do a little bit later on. So I want to point that out here. The other thing I want to point out is really this is just asking us to plug a value in. But keep in mind the time difference that's here. See, this says this gives the population after x weeks because it doubles each week. And then this is asking us what's it going to be after 56 days. So keep this in mind. Our x value, the way this equation is written, this is written in terms of weeks. So if we want to plug values into it, those values have to be in terms of weeks. Okay? So the first thing I need to do is I need to convert this to weeks. So 56 days, I would divide it by 7, and I'd find out that that's 8 weeks. Okay? Now that I have it in the right time signature, now I can plug it in. So I want to do f of 8. I want to plug this in, find out what it is at 8 weeks. So I'm going to raise that to a power. And really, this is just a job for my calculator. 2 to the 8th power times the 30. And when I do that, I find out that the population is going to be 7,680 beetles. So there's going to be 7,680 of them after 8 weeks. And that's it.